Welcome to Theory of Computation. I am Dr. Sarmad Abbasi and I would be teaching this course. The Theory of Computation is a very important course in computer science. In fact, it should be the first course that should be taught to computer scientists. However, this course is so basic, so fundamental, and so abstract that it's usually taught at graduate level or at the senior undergrad level. This is going to be a graduate level course. Well, as you're doing a master's degree in computer science, you must have taken several courses in computer science. So, let me tell you about how this course is similar and different from the courses that you've already taken. A very important component of computer science courses is programming. When you take a course in numerical analysis or data structures or algorithms, usually you design algorithms, you study algorithms, and then you implement them. You sit on a computer, you type out your programs, you compile them, you run them, and then you submit assignments. That's an extremely important ingredient of almost every computer science course you take, whether it is operating systems or compilers. However, this course is going to be very different. This course is not going to involve any programming. So that's the good news. Well, what's the bad news? The bad news is that this course is going to be more difficult than any other course you've taken, because the only tool, the only thing you would be asked to do in this course is to use your mind, is to think and think very hardly and deeply on extremely fundamental questions. As the name suggests, Theory of Computation is a very foundational course in computer science. In this course, we are going to ask questions which are so deep that we were not asking them when we were learning basic computer science. In basic computer science, you were learning how to play with computers, how to make them do something useful. In this course, we will ask questions like, what is a computer? What can a computer do? Are there any limitations of computation? Can we solve every computational problem? These are extremely deep and philosophical questions. Not only they are philosophical, but they are also extremely foundational questions. Of course, these questions can be answered in many ways, but Theory of Computation is going to insist that we give extremely precise answers to these questions. How do you give extremely precise answers to questions like, what is an algorithm? What is a computation? Well, the idea is that we are going to use mathematics. We're going to use the language of mathematics to define concepts in computer science very, very precisely. So all the objects that we will define in this course are going to be precise mathematical objects. And these objects are going to be either models of computations, or they would deal with computer science in one way or the other. Once we get precise mathematical definitions of all the concepts, then we will be able to ask these questions in a very precise way. Every question will be posed as a mathematical question in an extremely precise way. And then we will insist on extremely precise answers. You would see that we will be able to satisfactorily give answers to many of the questions that I have told you. Of course, for some of the questions we won't be able to answer them to our full satisfaction, and they would become open problems, problems that you, I, and other computer scientists can ponder upon. So that is the rough idea of this course. The idea of this course is to ask very, very fundamental questions and try to answer them with mathematical preciseness. One tool that we're going to use is mathematical proofs. So, in this course, if we say a statement, not only that statement is going to be precise to the dot, that is given through the language of mathematics, it's going to be an extremely precise statement, but also we will insist that we find a proof of that statement. Thus, the validity of statements that we prove in this course cannot be questioned. They will be accompanied by a rigorous mathematical proof. So, in this course, you will have to work hard not on writing elaborate and long and complicated programs, but working out subtle details of mathematical proofs, the finer points of mathematical proofs. You would also be required to construct your own proofs. I would be giving you problems, exercises, which would be asking you to prove one thing or another. So, what you will do is write down a solution which would be a mathematical proof. So, this is a course that's going to be heavy on mathematical rigor. And for that, what you need to do is brush up your basic mathematics, especially the course that you took in discrete math, and especially the sections that dealt with proofs, logic, and combinatorics. We would be needing all those tools. Let us look at the overview of today's lecture. In today's lecture, all I'm going to do is introduce you to this wonderful subject that we call the theory of computation. This is one of the most exciting subjects in computer science. Not only it's exciting, but this subject is extremely active at the research level. I think it would remain active as long as computer science remains as a mainstream science, because it asks such fundamental questions. And the amount of knowledge we have acquired in this subject is very limited, and our wish list is extremely long. So, let's look at the overview of today's lecture. Today we will start talking about the story of computation, and after that we will discuss what theory of computation is, basically what is computability theory. From there on, we'll talk about computability and logic, which is actually the relationship between computability theory and the very exciting field of mathematical logic. In the end, I would tell you a bit about complexity theory. So, today's lecture is going to be an overview of what is to come in the next 45 lectures. Of course, you will not be able to understand this lecture completely and appreciate it fully, but it would give you a sort of a flavor of what is to come in the next 45 lectures. I hope that today's lecture will get you excited and you would be able to enjoy the rest of the course. So what I want to do is today talk about the story of computation. The story of computation is a story that can be told in many, many different ways. A historian will tell it in a different way. Somebody who's a software engineer would tell you the story in a different way. A hardware electrical engineer or a computer engineer who actually builds computers will tell you this story in a very different way. And a theoretical computer scientist like myself, who views of computation as an extremely abstract thing, as an extremely abstract subject, will tell you this story in a very different way. So, when you hear somebody tell you a story of computation, remember that they are only telling you a story, their version, which is tainted with their biases. There is no the story of computation. If one were to try to understand the story of computation in its entirety, that would take a very long time, and that person will end up becoming a historian, perhaps a professional historian. So let us start looking at our story of computation. Let me ask you to do one thing before we go to the story of computation. I want you to pick up a piece of pen and in 30 seconds draw the model of computation, the earliest model of computation that you can think of. So pick up a pen and a paper and as quickly as you can jot down the figure that comes to your mind of the earliest computer that you think existed. And look at that picture and see how does it look like. So take no more than 30 seconds, and I have been talking for 30 seconds now, so your picture should be done by now. Draw a picture of the earliest computer that comes to your mind. Well, look at the picture, and I did this exercise myself. And I came up with not one, but 2 pictures in 30 seconds. And here are the pictures that I came up with. Yes, there were 2 earliest computers. And here is the picture that I came up with. And as you can see, what I have drawn is 2 human beings. Human beings were the earliest computers. So in some sense, the story of computation is as old as human beings themselves. No one will be able to tell us when was the first algorithm devised or when human beings started computing. That story is as old as time. So one of the first known mathematical artifacts to human beings is called the Limbobo bone. That is a piece of bone which is 35,000 years old. And historians and mathematicians believe that this bone was actually used as a mathematical device. Somebody was putting marks on it and actually doing unary addition or of some kind. So mathematical problems and computers, very simple devices, are as old as 35,000 years, and that's just the only recorded piece we know. They may be much older than that. So as far as mathematics, computing is concerned, that is as old as you may want to get. That's as old as human beings itself. I do not want to pursue more in this direction. A lot of biologists will tell you that animals also compute. Some animals can keep track of how many eggs there were in their nests and so on and so forth. So one can push this idea and say, well, computer science is even older than human beings and so on and so forth. But that's not the direction that I want to take this discussion into. If you're more interested in that kind of reasoning or that kind of a story of computation, of earliest devices, of earliest birds that can count and things like that, you can search the web. There's a host of knowledge available for you. What I want to do is quickly get to modern computers and then actually talk about mathematical ideas in computer science. So after these kind of bones which were used for computing devices, the next stage in human history of computing devices is called the abacus. The abacus was a next device, and here's a picture of a typical abacus. Abacus were discovered in Mesopotamia and also in China, and they are pretty old. After that, another computing device was invented in the 1600s, which is called the slide rule. Some of you may have seen a slide rule. Here is a picture of the slide rule. A slide rule is a ruler which is much more complicated than the ruler that you used to use when you were a kid. This ruler was actually invented after the discovery of logarithms. So tally sticks like the Limbobo bone were the earliest computing devices. Earliest known one is 35,000 BC, so it is about 37,000 years old. There are clay tablets that were used by human beings to count livestock, etc. And after that, about 2,500 years ago in Mesopotamia and China, we had abacus. These were the earliest known computing devices. And around 1620, when John Napier introduced the concept of logarithms, the slide rule was invented somewhere around that time. So that's the story of how we got computing devices. And after that, there's the story you must have read in any computer science book, how vacuum tubes were used, how first mechanical devices were used to do computing. There was the Babbage's engine, and there was the analytical engine, and how slowly we moved on to calculators, and then computers with punch cards, and then modern electronic computers. But the story that I'm interested in is the story of computational thought, of computational ideas. How did those ideas evolve? More than physical devices, we are interested in the history of concepts in computing. We are interested in very basic questions. Let us ask the following more important question. When was the first algorithm devised? This is a very difficult question, since algorithms were not studied the way we do them today. Today, the study of algorithms is an extremely systematic matter. In fact, algorithms is one of the most fundamental courses in computer science, and it's one of the most active fields in computer science research. Today, we have several thousand, if not tens of thousands of people who would say that they have dedicated their lives to the study of algorithms. For example, a great computer scientist, Don Knuth, whose name you must have heard, says that he has dedicated his life to the subject that is called the design and analysis of algorithms. So today, algorithms is a very systematic field, but that was not the case long time ago. Perhaps the first algorithm that human beings devised was some kind of unary addition. If they placed 5 marks and they had 5 eggs and they added one more to the pile, they would put another mark. And that is an extremely simple algorithm, and that's probably as old as teledevices or as old as human history itself. The concept of algorithms is also very well developed in Euclid's school. You must know Euclid had an amazing school of mathematics in Greece, which was around 2300 years ago. So in this school, he used to teach geometry and other subjects, but they had very precisely devised some algorithms. And one of the most celebrated algorithms is the Euclid's algorithm for computing the greatest common divisor, or it is also called the highest common factor of 2 numbers. You must have studied this algorithm when you were a kid. You remember you would be given 2 numbers and asked to compute the HCF or GCD, and you take the larger number and divide it with the smaller one, and then if a remainder was left, you will bring out the smaller number and put it down here and continue the division, and you'd keep doing that till you got a 0 remainder. And the last number that you divided was the answer. So this is an algorithm that everyone is taught in elementary school, and this is Euclid's algorithm. I call it one of the first non-trivial algorithms that is taught to students because it is not clear at all why does the Euclid's algorithm compute the GCD. In fact, if you look at the definition of the GCD, it doesn't seem to have much to do with this procedure. So this is what I call a non-trivial algorithm, a procedure that miraculously seems to produce the right answer. Well, there is a proof which demystifies Euclid's algorithm. The proof says that the Euclid's algorithm correctly computes the GCD. And we need that proof in order to be sure that this is a correct algorithm. Nevertheless, Euclid's algorithm is one of the earliest examples of a non-trivial algorithm that performs a task, and in fact, it is such an important algorithm that it was studied many years after Euclid invented it. Many modern computer science papers are about Euclid's algorithm, and several papers have been written which suggest improvements on Euclid's algorithm. However, it still remains a classic, and it still remains something that we awe and wonder at. Another place where we find a strict concept of algorithms in Greeks is the following. Greeks were very interested in constructions by ruler and a compass. These are examples of precise algorithms. The elementary steps are well defined and the tasks are well defined as well. You remember when you were studying geometry in high school or metric level, you used to do, for example, you would bisect an angle. So you would be given an angle, a compass and a ruler, and what you would do is you take the compass and make an arc, and then you will go and make 2 arcs, and when they crossed, you would join that line with the center of the angle, and then you would say that I have bisected this angle. This was a mechanical procedure, a process that you could follow without any intelligence, and the end product of the process was that you had managed to bisect an angle. This concept of ruler and compass constructions, or being able to do things with a ruler and compass, is also a very precise notion of having algorithms, where each elementary step is well defined and the goal is well defined, and the algorithm is a series of instructions that takes you from the initial configuration, which is the input, which may be an angle, to the final configuration, which may be the angle bisected, through an application of well-defined elementary steps. So the Greeks had a very precise notion of algorithms, although they did not really call them algorithms. So one of the most important questions in theory of computation is, what is a computation and what is an algorithm? If you take an undergraduate algorithms course, usually you are told that an algorithms is a recipe, it's a series of instructions which is well defined. It's a process that you follow in order to accomplish certain tasks, and it's a process that always ends in a finite number of steps and gives you the right answer. For example, bubble sort is an algorithm. It is a process which has an elementary step of comparing two elements and swapping, and it uses those two elementary steps in a very precise way, and what it does is, in the end, when you apply bubble sort, after a finite number of steps, you get the list in a sorted order. So bubble sort qualifies to be an algorithm. On the other hand, if I were to give you a process in which I say, solve such and such partial differential equation and then do this and this, you would immediately stop me and say, well, I have never taken a course in partial differential equations and therefore I don't know how to solve them. So that instruction does not constitute of an algorithm. I will have to teach you how to solve partial differential equations, which is a very difficult task, in order for this description to become an algorithm. So a very important question is, what is an algorithm? So let's go and find out in history how this question came about. And we will see that when we started asking this very fundamental question, that led us to amazing developments in computer science and the conceptual development of computer science. The story starts from the year 1900, when there was an International Congress of Mathematicians. The International Congress of Mathematicians is a 4-yearly meeting that happens where all the best mathematicians of the world meet, and they discuss ideas and read papers and look at what work has been done in the past 4 years, and of course challenge each other with problems. Well, in the year 1900, which was a very special year because it was the beginning of the century, a very, very eminent and deep-thinking mathematician named David Hilbert was asked to give an inaugural speech. And David Hilbert was an amazing mathematician. And his speech is a fascinating speech because rather than going over what was accomplished from 1800s to 1900s in mathematics, he simply asked what the next century, what the mathematicians should try to accomplish in the next century. And he did that in a very, very beautiful way. He did that by posing problems to mathematicians and said, here are 21 problems that I think are very important to mathematics, and we should try to solve them in the next century. So he gave a list of 21 problems, which of course became prized problems. If you ever solved one of Hilbert's 21 problems, you were a very proud mathematician, you were a very satisfied man, and of course you were famous too. So Hilbert gave 21 problems to mathematicians and said, why don't we try to solve them? Well, his problems spanned several areas of mathematics: analysis, logic, foundations of set theory, geometry, and so on. However, one question the 10th problem is very interesting to us. You must be wondering, why am I talking about a mathematician's speech in 1900 when this is a computer science course? Well, that's because Hilbert's 10th problem had to do with computer science. Let's look at Hilbert's 10th problem and let's see what it asks. The exact words in which Hilbert's 10th problem was phrased is the following. Given a Diophantine equation with any number of unknown quantities and with rational integral numerical coefficients, devise a process according to which it can be determined in a finite number of operations whether the equation is solvable in rational integers. Well, this statement of Hilbert's 10th problem is overwhelming to you. You do not understand what a Diophantine equation is, what are rational integer coefficients, and so on and so forth. Let's leave all of that out and look at this statement once again and concentrate on the words that I've bolded out and just examine and see what Hilbert is asking. He's saying to devise a process according to which it can be determined in a finite number of operations. So the two important things are that we are looking for a process which determines in a finite number of operations. Hilbert was asking for an algorithm. The Hilbert's 10th problem is asking mathematicians to devise an algorithm. So even though Hilbert did not know it himself, he was asking a computer science question. Well, one of the very interesting things about Hilbert's problems, and Hilbert himself was the kind of a man he was and the kind of things that he could envision. For example, Hilbert's 21 problems, well, almost all of them were solved within 100 years. Some of them took 3 years to solve and the others took about 70, 80 years. So in some sense, the challenge that Hilbert had given to mathematicians was the right challenge. He had gauged the difficulty and the importance of his problems very, very beautifully. All these problems were almost solved after 100 years. That's an extremely interesting aspect of Hilbert's foresightedness and his vastness of his imagination. He could predict, in some sense, where human thought would be in 100 years. Well, let's leave that aside and let's get back to what interests us here the most. One of Hilbert's 21 problems, and that is the 10th problem. Let us examine the 10th question in modern language. So I will change the language of this a little bit so as to make it easier for you to understand, but this question is equivalent to Hilbert's 10th problem. Let's look at a polynomial in many variables. So for example, we have a polynomial x squared plus y squared is equal to 0. Then we have a polynomial x squared plus y squared is equal to z squared. And then the polynomial given below to you is a different one, ax plus by plus z cubed plus 17d squared is equal to 1, 4, 5, 6, 7. These equations are called Diophantine equations. What is important about them is all the numbers that you see are integers, there are no fractions involved. So we will call them Diophantine equation. What we want to do is ask if there is a solution for these equations in positive integers. So for example, here the first equation cannot have a solution in positive integers because the sum of two positive integers will always be positive. Let's look at some more examples. The equation x squared plus y squared is equal to z squared has solutions in positive integers. X equals 3, y equals 4 and z equals 5. So this equation has solutions. On the other hand, let me give you another equation which is x squared plus x plus 2y equals 39. This equation does not have a solution. Well, let me convince you that x squared plus x plus 2y equals 39 has no solutions. The reason is 2y is always going to be even. So for me to have a solution, I would want x squared plus x to be odd. Well, if x is odd, then x squared is odd, and so x squared plus x will be even. So any odd x would not give me x squared plus x as an odd number. Similarly, if x is even, then x squared is even and x is even, so their sum will again remain even. Therefore, on the right hand side of this equation, no matter what numbers I put, I'll get an even number on the left hand side, and the right hand side of this is 39, which is an odd number. An odd number can never become equal to an even number. So by looking at this equation, I was able to tell that there are no solutions to this equation. So some Diophantine equations have solutions, some of them don't have solutions. Now this is what Hilbert's question is. Hilbert's 10th problem was the following problem in computer science. Can we write a program that will take a Diophantine equation as an input and tell us, after doing a certain amount of computation, if the equation has a solution in positive integers? He was asking for an algorithm. He was asking for a computer program. Can you write a computer program in C++ which will take Diophantine equation as an input, and after computing for a certain amount of time will tell us whether this equation has a solution in positive integers or not? Of course, each equation either has a solution or not, so there is always a well-defined answer to this question. The problem that Hilbert gave was, can we find a mechanical procedure, an algorithm that would lead us to the right answer? That kind of a program would have been very useful for mathematicians. They would not have to spend their time solving Diophantine equations. They could just give it to a computer and let the computer work on it. Although at Hilbert's time, there were no modern computers, but in principle, they could give it to a computer which could be a graduate student like you, who could mechanically work out, go through the instructions and tell them whether a given Diophantine equation has a solution or not. Well, Hilbert's problem was solved 70 years later by a very young Russian mathematician called Yuri Matissevic. In fact, I think he was about 21 or 22 years old when he solved Hilbert's 10th problem. A solution to Hilbert's 10th problem would mean that mathematicians could solve Diophantine equations almost mechanically. It took 70 years to solve this question, and Matissevic was able to solve Hilbert's 10th problem. What was Matisevic's solution? Did he invent an algorithm? No. So Matissevic did not invent an algorithm which could tell you whether a Diophantine equation had a solution or not. So how did Matissevic solve Hilbert's problem? Hilbert had said, find an algorithm which will tell us whether a Diophantine equation is solvable or not. And Matissevic did not find such an algorithm, so how did he solve this problem? Well, that's where the answer becomes more interesting than you would have hoped. Matissevic proved that Hilbert's 10th problem was unsolvable. There is no algorithm that can tell if a Diophantine equation has a solution in positive integers. Note that to understand what he did is not that easy. Matissevic did not say that he is not smart enough to find a solution. He did not say that he is not smart enough to come up with an algorithm. That many people were not able to come up with an algorithm and was a trivial thing. He was able to prove that no such algorithm existed. He was showing the impossibility of the existence of an algorithm. So Matissevic showed the impossibility of the existence of a mechanical procedure that could solve Diophantine equations. So in some sense, Matissevic was saying that mechanical procedures cannot solve general Diophantine equations. This is a very, very difficult problem. Well, this is perhaps the first time in computer science that you have heard that a problem is impossible to solve, that an algorithm is impossible to design. And it's not impossible to design because it's too complicated, but it's not impossible to design, period. It's not impossible to design as a fact, that no one can ever design such an algorithm because such an algorithm does not exist. This is an extremely deep fact. Impossibility proofs are not very uncommon in mathematics. Let's look at some of them. You must know that it's impossible to write square root of 2 as a ratio of two integers. All of you know that square root of 2 is an irrational number, and I hope that each one of you have seen a proof that square root of 2 is not a rational number, that it cannot be written as a over b, where a and b are positive integers. So that's a proof of impossibility in mathematics. Another proof of impossibility that you are perhaps told, but you have never proved, is the following. It is impossible to trisect an angle with a straight edge and a compass. This is another proof of impossibility from mathematics. It's taught to students who take a course in abstract algebra, and if the instructor is sufficiently interested, this proof is sometimes included in there. But nevertheless, mathematicians are very comfortable with the idea of impossibility of things. It is impossible to trisect an angle. It is possible to bisect an angle with a straight edge and a compass, but no mechanical procedure can trisect an angle in finite number of steps. Another proof of impossibility in mathematics is it is impossible to cut a regular tetrahedron and put the pieces together into a cube of equal volume. So, if I give you a regular tetrahedron and ask you to cut it up into a billion pieces and put them together so that they become a cube, well, that's impossible to do. In fact, the solution to this problem is also a solution to one of Hilbert's problems. So, mathematicians are very comfortable with the idea of impossibility. Yuri Matissevic has a theorem of that kind for computer scientists. It's impossible for anyone to devise an algorithm that checks whether a Diophantine equation is soluble in positive integers or not. In order to prove that an algorithm cannot exist, we must have an exact and mathematically precise definition of an algorithm. That is what is needed in order to show mathematically that an algorithm does not exist. Once the precise definition of an algorithm is given, we can start arguing mathematically about it. See, in order to prove square root of 2 is irrational, I must first define what are rational numbers precisely. If I have only a vague notion of what is a rational number, then I will not be able to concretely argue that square root of 2 is irrational. On the other hand, once I have a definition, a mathematical definition of what a rational number is, then I can try to argue and prove that square root of 2 is not a rational number and therefore irrational. So, similarly, if I want to show that an algorithm doesn't exist, I must have a precise and exact definition of an algorithm, not an intuitive notion, but a very mathematically precise definition. And of course, Matissevic needed that definition in order to construct his proof. Well, where did the definition came from? Luckily, the mathematical notion of what an algorithm and a computation is was already developed for Matissevic. Let us ask a more fundamental question in theory of computation, that is, what is an algorithm and what is a computation? So this is a fundamental question that we need in order to even state Matissevic's theorem, in order to even tackle Hilbert's 10th problem. Luckily, this thing was already done before Matissevic. In fact, this kind of work was done much earlier in the 1930s. The seed of the answer to this question were also sown by Hilbert himself. In 1928, Hilbert wanted to systematize all of mathematics and had posed the Einstein-Young's problem. That's a very long name for a problem, but that's what he posed. He wanted an algorithm that would take a mathematical assertion and decide if the assertion was true or not. That would be an amazing algorithm if it existed. So what Hilbert wanted was that all of mathematics should be systematized and mechanized. He was asking mathematicians to devise an algorithm. And this would be an amazing algorithm. What you would do is you will take a mathematical assertion a mathematical statement and give it to this algorithm. This algorithm will analyze the mathematical statement and tell you if the statement was true or not. That would be a truly spectacular algorithm. So the Einstein-Young's problem was one of the most important problems to have ever been posed in mathematics. Well, the problem with this problem was that once again, no such algorithm existed, as it was shown by two brilliant people, Alonzo Church and Alan Turing. In 1936, Alan Turing and Alonzo Church showed that this problem was unsolvable. The two most famous papers in this regard are one by Church, which is titled An Unsolvable Problem in Number Theory, which shows that this problem is unsolvable, and Alan Turing, the paper is titled On Computable Numbers with an Application to the Einstein-Young's Problem, and this also shows that this problem is not solvable. In Alan Turing's paper, Alan Turing introduces the notion of mechanical machines, mathematical machines that take input and perform precise computations and then produce some output. We now call these machines, by honoring him, we call these machines Turing machines. But these were precise mathematically defined objects. And in fact, Alan Turing argued that any algorithm must be a Turing machine, or must be one of the mechanical machines that he was defining, which we now call Turing machines. We will work with not Church's model as much as Turing's model. Turing came up with an idea of computing machines that we now call Turing machine. He proposed that every computation that we perform mechanically could be performed by a Turing machine. The good thing about a Turing machine was that Turing machines are not intuitive notions like that of an algorithm. It is not an intuitive notion, but they are mathematically defined objects. Thus, one can prove things about Turing machines. One can also prove their existence and non-existence. One can study them with the tools of mathematics and make precise claims about them. So, what Turing had done was come up with a mathematical definition of the intuitive notion of an algorithm. He captured this intuitive notion with mathematical preciseness. And mathematically defined objects are wonderful because we can make precise statements about them, we can prove things about them, and we can say things about them definitively. And that's what Turing had accomplished. In that same paper, Turing showed that Hilbert's problem that he had asked for in 1928, the Einstein-Young's problem, is not solvable by Turing machines. Thus, there is no algorithm which can tell you whether mathematical assertion is true or not. So, he had already established at least one problem for which there was no algorithm, no Turing machine. Turing in the same paper showed that a very important problem called the halting problem cannot be solved by an algorithm. This was a breakthrough. It showed that there are mathematically defined, precise problems that have no algorithmic solutions, thus showing us that some problems cannot be computed. One can show that certain problems are uncomputable. That was Turing's contribution to computer science. He gave us a precise model of computation, and then he also showed us how to show at least that some problems are not solvable by algorithmic means. A tremendous breakthrough in thoughts. So, what we will be doing is studying theory of computability theory or theory of computation. And a large part of this course is going to be asking questions of this form and answering them in a mathematically precise way. So let's have a look at what are we going to study in computability theory. Computability theory will deal with the following kinds of questions. And I have written short answers for you, but we will go through them as we proceed in the course. The first question we will ask is, what is a computation? Can we come up with a precise definition of an algorithm or that of a computation? And the answer to this question is yes, we can. Yes, we can capture the intuitive notion of algorithms in a mathematically precise way. Alan Turing has shown us this, and we will use his model. The second question we'll ask is, can everything be computed? Is it true that any mathematical, any computational problem I write down, you can find an algorithm to solve that problem? The answer to this question is no, as Alan Turing showed us initially, that the halting problem is undecidable. There is no algorithmic solution to that problem. So we will be able to answer this question also in a very precise way. Another important question that will come to our mind is, can we characterize problems that can be computed? The answer to this question is hard, but in certain cases we can identify them, and in certain cases we can prove that problems are not computable. So, the computability theory has a sound foundation, has a reasonable amount of a body of literature, amount of techniques that we have developed that allow us to look at problems and use those techniques and be able to tell whether that problem is computable or whether we can design an algorithm for it or not. Or when we start suspecting that a problem is not computable, we have a reasonable number of techniques we have developed which allow us to show that a given problem is not computable. So, computability theory does give a reasonably satisfactory answer to this question. Yes, in most of the practical cases or the cases that arise around us in mathematical contexts, we can tell whether a problem is computable or not, but of course, not always. We will study computable and uncomputable problems in different areas. These problems will come from language theory. They will be problems concerning sometimes numbers. They will be problems concerning Turing machines and so on and so forth. There will be certain problems that we look at in logic, from mathematical logic, and ask which one of them are computable and which one of them are not computable. We will also study computability and logic, and we will prove what is known as Gödel's incompleteness theorem. Well, Gödel's incompleteness theorem is not really a goal of this course, but it is a fascinating theorem in mathematical logic, and it essentially says that in any axiomatic system that include numbers, there are always statements that are true but not provable. This theorem is extremely profound. In some sense, it says that there are always truths which we cannot prove. So in some sense, we cannot reach all the truths that there are in mathematics. This is a beautiful theorem in mathematical logic, and we will actually come up with a proof using computability theory. And that's going to be a very exciting part of this course. After that, we will move our attention to a more modern version of theory of computation, which is called complexity theory. Complexity theory does not ask if we can compute problems using algorithms, but how long does it take to compute? How many resources does it take to compute? So complexity theory looks at computation in a more practical framework. Now what we want is not just algorithms, but efficient algorithms. So complexity theory is much more practical than computability theory. The basic idea is now we want to not just algorithms, but efficient algorithms to solve problems. In complexity theory, we will deal with the following questions. Given a problem, can we devise an efficient algorithm to solve that problem? So now we are interested in efficient algorithms. Can we characterize problems that have efficient algorithms? So we would like to identify problems that we can solve efficiently. Can we characterize problems that are on the boundary of being efficiently solvable and intractable? So can we actually somehow be able to tell that this problem is on the boundary of being practical but it's just becoming intractable? Can we somehow capture those problems? Because remember, it is no use being able to tell that a very hard problem does not have an efficient algorithm. What we would like to know is, what is it that makes problems hard? What is it that makes it just cross the barrier of being efficiently solvable and makes it interactable? That's what the goal of complexity theory is, or one of the goals. Can we prove that problems are intractable? So now we want to prove that there are certain problems for which there are no efficient algorithms. Can we do that? That's a very big open question in complexity theory. Can we prove that certain problems that are practically significant are intractable? That is an extremely important question. Lastly, is there a unified theory of problems that are hard to solve? We will explore all these problems in complexity theory. Not only that, we will study two extremely important theorems in complexity theory, or rather one theorem which was discovered by two extremely important scientists in complexity theory called the Cook-Levin theorem. That theorem will give us a extremely concrete problem which, if it were solved efficiently, would lead to an efficient solution for thousands of problems. This is going to be the theory of NP completeness, and this would lead us to an extremely celebrated question in computer science called the P versus NP question. The P versus NP question is one of the most important questions in computer science today. If anyone were to solve this problem, they will get $1 million from the Clay Mathematical Institute. Well, I personally think that the $1 million award is a very puny award for a problem which has such far-reaching consequences. We will actually concretely define this problem and see why it is so celebrated and why its solution is so important in computer science. Well, all these exciting developments, all these exciting theorems and theories await for you in the rest of this course. We will start this course next time by precisely defining Turing machines. I will see you next time. Thank you and goodbye.